Look, if you're building systems meant to scale globally, understanding the network edge isn't just a nice-to-have optimization. It's literally non-negotiable. Welcome to this explainer. Today, we're stepping way out of the local dev sandbox and looking at the brutal realities of distributed systems. We're going to break down exactly what separates junior guesswork from true, authoritative, senior backend architecture.
Let's dive right into a scenario that literally keeps engineering managers awake at night. Picture this production nightmare. Your synthetic tests are perfectly passing. Your custom infrastructure metrics, glowing green across the board. Everything looks absolutely pristine on your monitors. But an entire continent of users, let's say Australia, is staring at blank pages. How does this even happen? And more importantly, how do you debug it when your own monitoring tools are actively lying to you?
Well, to answer that, we need to look at our first major concept. Section 1, the regional edge nightmare.
You really see a stark contrast in troubleshooting methodology here. When something goes wrong, juniors might joke about the scream test, turning off a server or a service just to see who complains. Listen, in an enterprise environment, that is a career-ending move. Senior engineers, they don't guess. They rely on network telemetry. By analyzing cloud provider flow logs, they build a mathematical, flawless dependency graph of the traffic flow way before they ever touch a single node.
So, back to our Australian outage. Why are your dashboards green while a whole continent is down? It usually comes down to the architecture of your observability. See, synthetic tests often run from a single centralized region, like US East 1. Global metrics naturally average out, which completely hides localized routing issues. So if a local CDN node in Sydney has a corrupted cache, those US-based tests will literally never see it. They'll confidently report 100% uptime while your actual users are failing.
The absolutely crucial point here is that to see what your users actually see, you have to deploy global probes. These are diagnostic tests executed from every single geographical region where you have users, specifically designed to test that last-mile experience. Look, if you aren't testing from the edge, you simply aren't testing reality.
Let's move right along to Section 2, CDNs and partition tolerance. This gets into the fundamental physics of distributed systems.
If you're building for the edge, you have to respect the CAP theorem. And in a global context, partition tolerance is an absolute mandate. Basically, partition tolerance is a system's ability to keep functioning even when network partitions completely disrupt communication between your nodes. Because in the real world, someone trips on a fiber cable, a switch goes bad, or a BGP route flaps, the network will fail. It's not a matter of if, it's a matter of when.
Because of this unavoidable reality, global content delivery networks, or CDNs, are purposefully built to prioritize availability above all else. Eventual consistency is just the accepted trade-off. These highly available systems absolutely must keep serving content to worldwide users during a network disruption. A senior architect knows for a fact that it's way better to serve a user a slightly out-of-date, cached response than to just hand them a hard error page. You've also got to strictly differentiate your caching layers. Your application-level cache, like Redis, lives in RAM, gives you sub-millisecond access, and protects your primary database from melting down. But edge caching via CDNs is a totally different beast. It relies on global node distribution and header-based rules to serve data physically closer to the user. Serving a London user directly from a London edge node instead of forcing a trip all the way back to your New York origin, that drastically cuts round-trip times and offloads massive network egress costs. Now, let's talk about scalability and the performance trade-offs hiding in your metrics. Section 3, the tail at scale. Here is a hard truth you learn operating massive systems. The median, or P50 latency metric, is a total lie. It's a dangerous illusion. If you're only looking at your median response time, you're completely ignoring the tail at scale. I'm talking about that small fraction of requests that experience massive delays because of garbage collection pauses, noisy neighbors on shared hardware, or just random transient network congestion. And those tail latencies, they absolutely destroy the user experience for your most active, high-volume customers. To fix this, you've got to attack the network path first, simply because physics always wins. Undoing accidental network mistakes yields immediate, massive latency reductions. This means actively co-locating your chatty microservices in the exact same availability zone. It means reusing connections with HTTP2 or gRPC, heavily tuning your connection pools to avoid queuing, and switching from verbose JSON payloads to compact binary formats for internal service-to-service calls. To actively cut that long-tail latency, senior architects rely on an advanced technique called request hedging.
Basically, the system issues a second, identical request if the first one exceeds a strict percentile-based timeout, like your P95. The system then just uses whichever response comes back first, completely mitigating individual node lag. But hey, massive warning here. You absolutely must tightly balance request hedging with strict retry budgets. Otherwise, one tiny latency blip will trigger a storm of retries that can cascade into taking down your entire system.
But when things inevitably break, how you debug defines your seniority. Let's look at Section 4, debugging the network path.
When you're debugging edge routing, always use the golden metric of proxy debugging. You're comparing two crucial things, the upstream response time versus the request processing time. Think about it. If your upstream is returning data in 50 milliseconds, but the processing time at the proxy is 5 seconds, you instantly have your answer. You've mathematically proven that the backend application code is perfectly fast, but the proxy layer or the client network connection is severely struggling to buffer the data.
Then there's the incredibly frustrating semantic logic failure. This is when your app CPU is totally normal, your database is perfectly healthy, and your access logs are just filled with 200 OK successes, but your users are screaming that the app is broken. Always suspect semantic errors here. What's often happening is the backend is successfully returning a 200 OK status, but it's wrapping an empty JSON body or some logical error message that the front-end JavaScript literally has no idea how to handle. Now, check out this university research studying massive internet services. It challenges basically everything we usually assume about where these failures originate. Conventional wisdom says the backend database is your biggest risk, right? Since it's a stateful center of your application. But the data unequivocally proves that front-end and stateless application tiers are actually responsible for up to 72% of user-visible failures. And if we dig deeper into the root cause of these front-end failures, the data tells a very clear story. It's not hardware burning out or some deep, crazy algorithmic bug. The leading cause is overwhelmingly operator error. Specifically, misconfigurations applied by engineers during routine maintenance and deployments. Human error at the configuration layer is just incredibly difficult for standard redundancy mechanisms to catch and mask. Which brings us perfectly to our next core concept, Section 5. The deletion instinct. Senior developers don't write better code. They delete more of it. I absolutely love this quote. Complexity is your worst enemy in a distributed system. See, while junior developers try to prove their worth by adding clever abstractions, shiny new frameworks, and all these just-in-case features, senior developers are quietly removing thousands of lines of code that never should have existed in the first place. The practical impact of this mindset is staggering. In one documented real-world case, engineers took a bloated 3,000-line configuration system and reduced it down to just 200 lines of simple, highly focused code. The result? Bug reports dropped by a massive 80%, and system performance improved by 40%. Every single line of code is a liability that you have to maintain, monitor, and eventually debug. You really have to develop an instinct for strategic deletion. Every unnecessary function adds cognitive load for the next developer who touches the codebase. You need to aggressively delete unused features, kill those legacy API endpoints, and cleanly eliminate premature caching optimizations that were built for traffic loads that never actually materialized. And if you're importing some massive, heavy dependency just to use 5% of its functionality, drop it entirely and just write the 20 lines of code yourself. Smaller, simpler codebases are faster and infinitely more maintainable. Let's wrap this all up with Section 6, mastering the last mile. It's time to shift your paradigm. You simply cannot design backend systems in a vacuum. You have to design them for harsh network realities. So I want to leave you with this question. Are you going to keep relying on the amateur screen test, or are you ready to act like a senior engineer? Stop trusting median latency metrics. Start measuring your proxy deltas. Deploy global probes to measure the true last-mile user experience. And always, always remember, the most highly available, globally distributed code is the code that doesn't exist. Thanks for joining me on this explainer. If you got some value out of this, take these principles straight back to your architecture reviews this week. Keep building and keep deleting.